All right, we're going to wrap up chapter 3, talking about how to write and graph lines, right? How to write the equation of lines, how to graph linear equations. And then we're going to talk about a few theorems that are all about perpendicular lines. Okay? So, first things first, writing and graphing lines, writing the equations of lines and graphing linear equations. First things first, remember from Algebra 1 about the different forms of the equation of a line, right? There's standard form. Standard form looks like that, ax plus by equals c, where x and y are on the same side and you have some constant on the other side of the equal sign. We like this form because it makes it easy to find the x and y intercepts using that cover-up method. And so then if we have the x and y intercepts, then we know where the line is going to cross the x and y axes, and so we can graph the line pretty easily from there. Another very, very, very popular and very easy to use form is the slope-intercept form. That's what you remember most. Y equals mx plus b, where m is the slope and b is the y-intercept. Okay? Now, to write the slope-intercept form, we have to have the slope and we have to have the y-intercept. If you know the x and y intercepts, sometimes writing in standard form can be kind of a quick way to get the equation of a line. You'd need a little bit more information, but there are a couple of shortcuts there to write the equations of lines. Well, sometimes we don't have enough information to use a shortcut. If there's not a shortcut we can use, then what we like to do a lot at Center Grove High School is to use the slope formula. Okay? We use the slope formula for everything. Okay? We use it to find the slope. We also use it to help us to write the equation of a line, right? I'm going to show you how that works. Write the equation of this line in slope-intercept form. Okay? Now, we would need the slope and we would need the y-intercept to write this in slope-intercept form, right? So that is y equals mx plus b. Now, unfortunately, we don't know the slope. We do know the y-intercept. The y-intercept is right here. And remember that in the y-intercept, all y-intercepts have an x-coordinate of 0. So the number that we're really focused on with the y-intercept is the y-coordinate. So that's going to be your 4. So we can make this plus 4. But we need the slope. We don't have the slope. We can find it. And we find it. We can do it one of two ways. We can do just count rise over run if you'd like. So from this point down to this point, we have to go down. 1, 2, 3, 4, 5, 6. Down 6 is negative. And then we have to go right. 1, 2, 3. And so negative 6 over 3, and then we can reduce that down to negative 2 over 1, or just negative 2, and there's the equation of that line. Now, if you didn't have the grid to count, if you just had these 2 points, you could still find the slope, and we would use the slope formula to do that, right? The slope formula, which says subtract the y's over subtract the x's, where we go 4 minus a negative 2 over 0 minus 3. Remember that you have to go the same order in the x's that you did for your y's. So you get 6 over negative 3, which is negative 2 over 1, or just negative 2, and then we would plug it in for m in that slope-intercept form. Okay? So just kind of trying to refresh ourselves on how to write the equation of a line. Okay? Now, how we tie this into geometry is that we start talking about parallel and perpendicular lines. We talked about parallel and perpendicular lines and what their slopes would compare to in the last time. So we want to use that now. We're going to write the equation of a line passing through the point -1, 1, and we want our line to be parallel to that line, y equals 2x minus 3. Well, we know that we have to have a slope, and we're going to have a point. Now, it would be great if we had the y-intercept to plug into the slope-intercept form. Okay? But we don't know what that y-intercept is. So what the two very basic things we need to write the equation of a line is a slope and a point. Okay? A point on our line is the point that this line goes through, which is negative 1 comma 1. And we need to find out what our slope is. Well, the slope of this line is 2. And since our line is parallel to that line, then from last time we know that our line's going to have the same slope, 2. Okay? Now, we love using slope formula for everything. I know that if I write out the slope formula, m equals y minus y over x minus x, is that if I plug in the slope, which I know, and I plug in the point, and I only know one point on this line. So if I plug those coordinates in for this set of x and y's, y minus 1 over x minus a negative 1, then I can actually create a proportion that I can cross multiply and solve for y, and that would get me the slope-intercept form. So make this a plus. We're going to cross multiply. We get y minus 1 is equal to, distribute that 2 times x is 2x, 2 times 1 is 2. Now we're going to add 1 to both sides. And we get 2x plus y equals 2x plus 3. And so that's the equation of our line. That's going to be parallel to the line given to us. And we do a quick check to make sure that our equation makes sense by checking out the slopes and making sure that they're still the same. And they are. So we must be on the right path. Okay? Same thing if we want to write the equation of a line that goes through a point and is perpendicular to another line. Okay, we have to have a point, and right now our point is 2 comma 3, and we need a slope for our line. Now the slope for this line is negative 2. And because our line is going to be perpendicular, we know from last time that perpendicular slopes, lines that are perpendicular, have opposite reciprocal slopes. So I would have to flip it and switch it. So I have to take this fraction, negative 2 over 1, and flip it. And then change the sign, so make this positive 1/2. Now I can get back into slope formula and plug this point in for one of the xy combinations. And I always put it in that back end. I always want to put it in the x and the y that is in the end of the fraction, because it makes the math a little bit easier. Now we're going to cross multiply. Distribute your 2. 2 times y is 2y. 2 times negative 3 is negative 6. X minus 2 times 1 is x minus 2. Then we want to add 6. Then we want to go through and divide by 2. So we get y equals 1/2 x plus 1. And so again, a quick check that our slopes for our two lines do compare the way they need to, and they do. They're opposite reciprocals, so we must at least be on a little bit of the right path. Okay? All right. Now, what if we don't have another line to get the slope from, and we still want to write the equation of a line? So in this example, we have a gym membership, and it's plotted out. So the y-axis is the cost of the membership in dollars. The x-axis is the number of months that you've been a member. To write the equation of a line, we need a slope and then we need a point. Right? If we had a y-intercept, then it would be helpful. Unfortunately, we don't. I mean, we can see it, but we don't know exactly what it is. And so we're not going to try to use it. So we're back to needing a slope and a point. We actually have 2 points. One of the points in our line is 2 comma 231. If I had a slope, then I can go back to plugging in the slope and that point into the slope formula and gain the equation of the line that way. So let's go find the slope. The slope, again, is subtract the y's over subtract the x's. The y's are 363 and 231. The x's are 5 and 2. So we get 132 over 3, which is indeed 44, but I'm going to leave it as a fraction, 44 over 1. So now I have a slope, and I have a point. I want to use those two to help me come up with the equation of the line the same way I did the last two problems. Now we're going to cross multiply. Y minus 231. Distribute the 44. And then we add 231. And so y is equal to 44x plus 143. And that's the equation of your line. Okay? All right. Now, that's the equation of the line. The question is, what do those parts mean? What does the slope and the y-intercept mean? Well, the slope is supposed to tell you rise over run, right? But we need to add context to this, right? So from this point to this point, it tells you how far to go up and then how far to go over every time. So if your slope is 44 over 1, that means that every time we rise 44, we have to run 1. Well, in the context of the problem, if we rise 44, that means the cost is going up by $44. So the slope says that the cost increases $44 for every run, one run. And one run is 1 month. So $44 a month must be the membership fee. Okay? The y-intercept. You always end up on the y-axis when your x-coordinate is 0. And in this particular case, when x is 0, that means you have not been a member of the gym for any months. So why is there a number involved? Right? You haven't had to pay a monthly fee yet. So what's the 143? And the 143 it's the cost that you have to pay. It's the amount you have to pay even before you become a member. So it must be the initial membership fee and the initial fee to join the gym, $143. We'd want to be specific here in this context. The initial fee is $143. Right? Or the application fee, if you want to call it that. The application fee is $143. Okay? That's what slope and y-intercept mean, and you have to try to find the context in your problems. Okay? A quick review on graphing when we're in standard form. Okay? Again, the cover-up method. Standard form gives us the x and y intercepts. And if I want to find the x-intercept, I cover up the y part. And I solve that. Divide both sides by 3. And so x is 4. If I want to find the y-intercept, I cover up the x part. And I go solve for y equals 12, or y is equal to 3. That means on the x-axis, we hit it at 4. On the y-axis, we hit it at 3. And our line will go right through those 2 points. Okay? Quick review of the cover-up method. All right. Another use here of our lines. You can rent DVDs at a local store for $4 each. An internet company offers a flat fee of $15 per month for as many rentals as you want. How many DVDs do you need to rent per month to make the online rental a better buy? Okay. Well, we would need to come up with the cost structure for both, right? If you go to the store, you have to pay $4 every time you rent a movie. So if we let Y be the cost of rental and X be what we don't know, which is the number of DVDs, then we can come up with an equation of Y equals 4X. Right? 4 times the number of movies will tell you the total cost. And then the equation for an online rental, right? Well, they don't care how many rentals you make. They're going to charge you $15 a month. And so the question is, how many DVDs do you need to rent per month? So the cost for a month in the internet online rental is just $15. There's no variable. It doesn't matter how many DVDs you rent. So y equals 15. Now, we could actually use a graph to help us figure this out. If we go graph y equals 4x and y equals 15, then we're going to see when the cost is more for the store rental than it is for the online rental. So let's go graph them. Right? And here they are. The graph for y equals 4x is this line right here. Right? Your y-intercept is 0 since you don't see it. We're going to go up 4 over 1 to get to this point right here. And we can keep going to graph that line. Now y equals 15 doesn't have a slope, right? The slope is 0, so the line falls down to be horizontal, and it goes through 15 on the y-axis. So there's your line. Now where they meet is where the cost is going to be the same, right? Remember that y was our cost structure. It's how much we were going to have to pay. That's where they're going to be the same. So when does it make more sense to become an online member? When the cost becomes more for the store, which is this part right here. So you'd have to rent more than, well, you have to rent 4, because that's the place where the cost is more, or more. Okay? It's cheaper to rent locally. It's cheaper to go to the store if you're going to rent 3 or fewer. It'll be cheaper to do the online if you end up renting 4 or more. So that answers our question there. Okay? All right. Now, perpendicular theorems. Last piece here. We want to talk about some theorems that we know exist for perpendicular lines. Okay? First two theorems are here. 3.8. If two lines, and 3.8 doesn't really mean anything. The theorem, what the theorem says, means something. If two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. Now think about what that means. Two lines intersect, right? So G and H are intersecting, and they're forming a linear pair. Remember a linear pair, add to 180, right? They form a straight line, they add to 180, and if they are congruent angles, that means 1 and 2 would both have to be 90 degrees. If that's the case, then the lines are going to, of course, be perpendicular, because perpendicular lines, the definition says that they intersect to form right angle. Now, this theorem takes the right angle piece out of it. It just says that if you have two lines that intersect to form a linear pair of congruent angles. So if I want to use this diagram to show this theorem, I would want to use the symbols to write out the if-then portion of the theorem. So what this is saying is that if I know in this diagram that angle 1 is congruent to angle 2, then I would know that G is perpendicular to H, and never having to talk about right angles at all. And that's the point of the theorem. Okay? Theorem 3.9 here, or this guy says that if two lines are perpendicular, then they intersect to form 4 right angles. Okay? The definition says that if two lines are perpendicular, then they form a right angle. But it's not just a right angle, it actually forms 4, and this theorem talks about that. Now, to use this particular diagram, it's helpful to understand, or to write an if-then statement, so that you know what you would have to know to be true, and then what you could conclude. So from this picture, to use this theorem, I would have to know that A is perpendicular to B. So if A is perpendicular to B, then I would be able to conclude that angle 1, angle 2, angle 3, and angle 4 are right angles. Okay? All right, so trying to use these theorems. In this diagram, we know that AB and BC are perpendicular. What can you conclude about angle 1 and angle 2? And we want to use the theorem, right? I know the definition of perpendicular lines might help us, right? But that would only help us determine that one angle is a right angle. Here, the theorem lets us know that angle 1 and angle 2 are going to be right angles. Okay, and that's because we knew the lines were perpendicular. All right? All right. Next theorem says if you have adjacent angles, like angle 1 and angle 2 here, if you have adjacent angles and they're non-sharing sides, so this is the side of angle 1 that's not being shared with angle 2, this is the side of angle 2 that's not being shared with angle 1. If these guys are adjacent angles and they're acute and their non-sharing sides are perpendicular, then that means that angle 1 and 2 are complementary. Now that should make some sense if you think about it. Because if AB and BC are perpendicular, then they form this right angle. And that means that 1 and 2 would have to add to 90, which makes them complementary. But this theorem sort of slides past that whole adding to 90 piece. It just says if their non-sharing sides are perpendicular, then they're going to automatically be complementary. We can just jump to that conclusion. Right? So basically, from this diagram, what we'd have to know in this particular diagram is that AB, line AB, is perpendicular to line BC. And if we know that, then we can say that angle 1 and angle 2 are complementary without having to go through 90-degree angle. Okay? So I think it's helpful in a diagram to know what you need to know from this theorem in order to be able to conclude what you need to conclude. And so we need to use the proper symbols to talk about what this theorem says. Okay? Now, an example of this. We want to prove that if two sides of two adjacent acute, we want to prove that last theorem, basically. Right? So, we're going to set up a formal two-column proof. Okay? There are your statements. Now, I don't think in your notes you have the statements, so if you want to stop the video and write in the statements before we do the proof, go ahead. Okay, so I'm going to go on. ED and EF are perpendicular. How do we know that? Because it's given to us. It's right up there in the given. Now, how would we know that angle DEF is a right angle? Well, we have perpendicular lines, and angle DEF is the angle that's formed from those two perpendicular lines. So by the definition of perpendicular lines, we know that they form a right angle. So angle DEF is a right angle. Now, because we know angle DEF is a right angle, we know the measure is equal to 90. And that's by the definition of right angles. Okay? Now, next statement, angle 7 plus angle 8 is equal to the measure of angle DEF. Well, that's your angle addition postulate. Okay? Now, how do we get to the next line? 7 plus 8 equals 90. Well, if you look, we can take statement 3, and then it will allow us to substitute the 90 into the measure of angle DEF. So I'm going to use substitution here. Now, because 7 plus 8 equals 90, we know that 7 and 8 are complementary, and that's because of the definition of complementary angles. Okay? And there's your proof of that theorem. All right. A couple more theorems here for you. There's a lot of them, right? There's this perpendicular transversal theorem. And that says that if a transversal is perpendicular to one of two parallel lines, then it's going to be perpendicular to the other one, right? So what would that look like with this first picture here, right? We've got two parallel lines, H and K. This theorem says that if we know that J is perpendicular to H, right? That's what we're being given right here. And that H is parallel to K, that's what was given to us right here, then we can automatically conclude that J is perpendicular to K. Okay, so again, using the diagram to rewrite the theorem in symbolic form, it helps us kind of know what it is that we need to know, and then what we get to conclude from there. Okay? The next theorem says in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. It's almost like a reversal of the first one, right? But basically, if two lines are perpendicular to the same line, that means they're going to have to be parallel, right? You can almost link this back to the corresponding angle converse, right? Where the corresponding angles are congruent here, and so that means the two lines have to be parallel. But we specialize it down into right angles and perpendicular lines. So what would we have to know? And for this particular theorem, we'd have to know that M is perpendicular to P, and that N is perpendicular to P. And if we know that, then we can conclude that M is parallel to N. Okay? All right. A couple of examples to help strengthen those theorems. Determine which lines in this first one, if any, must be parallel. Which lines in this picture must be parallel? Okay? What do you think? Well, hopefully you're thinking that S and T would be, because they're perpendicular to the same line, line Q. So S and T need to be parallel. Are there any other lines that are perpendicular to the same line? And actually you see right here that line P and line Q are both perpendicular to S. So P is going to be parallel to Q. Okay? Now, next example. Is B parallel to A? B parallel to A. Well, they're perpendicular to the same line. They're both perpendicular to D. So yes. Next question. Is B perpendicular to C? And the answer to that is yes. And the reason why is because C is perpendicular to A, and now we know that A and B are parallel. So that means that B has to be perpendicular to C as well. So that's a yes. Okay? And we can use that information as we see fit. Right? Now, while we're talking about perpendicular, it's always, distance always comes into play with this, right? A couple more ideas here. The distance from a point to a line is the length of the perpendicular segment from the point to the line. In other words, if I'm standing here at A, and I wanted to measure how far away I am from line B, from line K, right? Then I'm going to measure a distance from point A directly at line K. So I'm going to walk at a perpendicular and measure that distance. Okay? That makes sense. It makes sense to measure the distance here, not to measure the distance all the way out here. Okay? Same thing between two parallel lines. The distance between two parallel lines is simply going to be the length of any segment that is perpendicular to both lines. So say point C, point D, segment CD. That's how we'd find the distance between those two parallel lines. Okay? That wraps up our perpendicular theorems. So apply those theorems in your homework. Homework's out in Canvas. Have that done next time.